All right, so limits with x approaching positive or negative infinity. Let's talk about that. So let's just kind of just go straight to the first example. I mean, there's all this like verbiage, but we know what we're trying to do. We're trying to investigate numerically, graphically, and then analytically if we could. So for example one, that's y equals 3, right? So here we go. So when x is approaching negative infinity, that's going to be the left end of your graph, right? We use these two limits for end behavior. And of course, that's the right end. So I think it's pretty obvious for y equals 3, what's going to be the limit in each of those cases? Yeah, that's it. Done. So if you have a constant, what's going to be the limit of the constant? The constant itself. There you go. So what this tells me is that the equation of any horizontal asymptote is y equals k. Does this have a horizontal asymptote? Actually, it does, believe it or not. This actually does have a horizontal asymptote. I know it's kind of weird. It does because horizontal asymptotes are purely about end behavior. What do the ends of the graph do for y equals 3? Y is 3. So even though we don't draw that, it technically does have a horizontal asymptote because correct, right. Sometimes it can. There are certain functions that may have two different horizontal asymptotes or piecewise that could happen. Um, but we can talk about that later. For now, we're just going to focus on more simple cases. So 1 over x, you guys should know this already. The graph looks like this, right? Should not be an issue. And we're only looking at the left and right ends. Where are the ends each going to? As x approaches negative infinity, what's the left arrow doing? It's going towards, and the right end's going towards, yeah. And also numerically, if you plug in large numbers, like if you plug in 1 over a million, that's a super small number, right? So numerically, we understand that, and we understand it over here, just graphically. So
I think you flip that. Starts negative and then goes positive.
I did flip it. Oh my gosh. Okay, no wonder there's confusion. I was doing negative 1 over x. My apologies. I actually saw a negative. No, just kidding. Yeah. So yeah, sorry, my apologies. So this does have a horizontal asymptote y equals 0. And again, it's not about a boundary. So horizontal asymptotes are not boundaries. They're simply what does the end of the graph, what did the ends of the graph do? That's all they ever are. So horizontal asymptote. So we're kind of rethinking how this is supposed to be. I mean, I'm pretty sure you were not told it was a boundary, but it's easy to assume that. But horizontal asymptotes are not boundaries we cannot cross. Instead, they represent what y approaches on the left and right ends of the graph. Hence, that's why we have x going towards positive negative infinity. So generally speaking, if you have 1 over x or 1 over x to the n power, where n is a constant greater than 0, what do you expect the limit to be in each of those cases on the bottom here? 0. There we go. That's it. Now, mind you, n has to be greater than 0, because what if you have 1 over x to the negative 2 power? Then what is that really? X squared, right? In that case, the limit as x approaches infinity or negative infinity is going to be positive infinity in that case, right? Because it's going up forever. So that there would not be horizontal in that case, right? Um, so this is what the true definition of a horizontal asymptote is. It's a limit definition. It's purely this. And by the way, it doesn't have to be on both sides. It could be on one side. You could do it as a piecewise limit, as a piecewise situation. So, or both. You're going towards both positive or negative infinity, and y is equaling some number as that happens. So sine x over x, we've seen this already. The graph looks like this. Kind of like a snake. And if I were to go to Desmos and plug that in. Desmos. Yeah, see, it kind of does that. Um, or I could actually, if you ever want to adjust the trig in terms of pi, go ahead and do this. And then make the step like, say, pi over 2. It always has an option if you ever want to do that. And you can see it's kind of leveling off on the far left and far right. Is it exactly 0? Sometimes, yeah, it is, right? Actually, there's infinite times this expression is 0. But if you think about as you get more and more to the right side, notice that the values above and below the x-axis get tighter. Like this curve is like starting to hug the x-axis, right? But is it exactly 0 the whole time? No. Does it hit 0? Sure. So it's all about approach. What is y approaching as x approaches positive infinity for this graph here? 0. Yeah. So 0 in each case. So this actually does have a horizontal asymptote because it follows the pure definition of a horizontal asymptote. The pure definition is the limit as x approaches positive infinity. If that is a finite value, if it's b, that is going to be a horizontal asymptote. And if we want to fill out the table, I mean, I know you guys know what's going to happen, but if I were to make that like say f of x, yikes, there we go, and do f of like 100, 1,000, 10,000, you get those really tiny numbers, right? If I plug in a negative, 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 whatever, right? Fine. Negative. So we don't need to fill those out because it's kind of trivial, but we know that these are super small numbers. I'm not going to actually write those out because that's just a waste of time. You guys get the idea. Because think about it. The top, what's the range for sine x? From what to what? No, the range for sine x, the output. What's the highest sine could be? 1, right? What's the lowest could be? And it oscillates, right? However, the bottom, as x approaches infinity, of course, is getting larger, right? Or if x approaches negative infinity, it is getting larger in the other direction, if that makes sense. Um, so you're going to see this separation between the top and the bottom, where the top is stagnant between -1 and 1, but the bottom is just going forever without bound, to positive infinity or negative infinity. That's why we get 0 overall for that fraction. From a numerical perspective, graphically, we see what's happening too. And notice the graph crosses horizontal asymptote infinitely many times. It's okay. It's not a boundary you can't cross. It's all about what is y doing as x approaches positive infinity. That's all it ever is. So in this case, we're going to say that's 0. And that's also 0. If you have sine kx over kx, it's also the same thing. Even if you had sine 5x over 5x, by the way, like say you had something like this here. Say you didn't have this extra k on the bottom. It's still going to be 0. Doesn't matter. We do know when x approaches infinity, then what's that going to be? This is a good review for your quiz. If it's kx over x, that's k. As x approaches 0. I changed that to 0. Yeah. Or if I get rid of both k's, then of course it's 1. If that's approaching 0. Right. So questions? We good? Okay. Yeah, just think numerically what's happening and look at the graph. That's really the best way to understand that. So let's keep moving. For this one, okay. Was a good one. I like this one a lot. Yeah, okay. Remember I told you things get a little complicated and there could be 2 horizontal asymptotes? Yes. Now we're talking about that. This is good. Before we fill out the table and look at the graph, and of course, there's a reason I have 2 blanks there because there are 2 horizontal asymptotes. Anyone want to take a stab as what A would be if x is approaching negative infinity? How about positive infinity? x gets really large. It's 2? Yeah, it's 2. How about the left side? It's -2. Yeah, I know. It's kind of trippy, huh? I know. What the heck's going on here? Why is this happening? Okay. Here's the reason why it's happening. You're square rooting x squared, right?
Okay.
Yeah, of course it's a +1. You're like, well, what about the +1? Who cares? Why is a +1 negligible? Why is it insignificant in this particular situation?
If the numbers get really big.
Yes, when x is approaching infinity, if x is like 1,000, who cares about a 1 here? 1,000 squared. What's 1,000 squared?
1 million.
1 million. It's like, for example, if you have $1,000,000, someone gave you an extra dollar, is that really going to matter? Not really. If you have $1,000,000, what? That's a dollar, whatever, just throw in the garbage, right? So that doesn't matter. So you think money, go on, if that helps you. That +1 is negligible, doesn't matter, right? But then when you square root thousands, sorry, when you square root 1,000,000, you get back to thousands, right? So what's happening is that when you square root this expression, it really is just going to be x. But technically speaking, it's not just x, it's the absolute of x, right? So you have 2x over absolute of x. We already see what happens when you have x over absolute of x. It's either 1 or -1. But because of the 2, that's why I get -2 and I get +2. So when x gets really large, that gets like 2 million, sure, or 2,000, whatever you want to call it. And that's 1,000 squared plus 1 square root is still 1,000. So 2,000 over 1,000 is 2. But if I plug in a negative number, does that ever become negative? If I square it and square root? No, it stays positive, but that's negative. That's why I get -2 for that. That's why I get 2 horizontal asymptotes. So if you just take a moment to think about it, hopefully it makes sense. Now, of course, we'll graph it. 2x over square roots x squared. Yeah, but I actually memorize that. I'm terrible at memorizing formulas. +1. Yeah, there we go. And I don't need trig anymore, so I could just get rid of that. Yeah, you can see it has 2 horizontal asymptotes. And if I were to say plug in 100 or -100, you get that. So I get like 1.999. Here I get -1.999. And pretty much the same thing over here as well. Now to analytically determine it, think best space next page. Oh, we don't. That's weird. Okay. I'll have to squeeze it in. Sorry about that. Huh. That's bizarre. To analytically determine it, what do you think we're gonna do? Yeah, good. Yes, piecewise. Excellent. 2x over and hold on, I gotta think about this one here. Yeah, trying to think x squared plus 1. How would I actually, because you can't write that as something squared, right? Because x squared plus 1 is not factorable. I think what we do is ignore. We call this an end behavior model. Ignore +1. So only focus on leading terms. And I actually messed that up, guys. I meant to write outside of x, not x squared. My apologies. Thank you. Yeah, I meant to write that. Yeah, that's because square of x squared. So when I write it piecewise, I get 2 or -2 when x approaches, when x is greater than 0 or when x is less than 0. So that's how you look at it analytically. And you're able to, or you should be encouraged to do analytical techniques if you're getting 0 over 0 or infinity over infinity, when you plug in whatever x is approaching into the expression. We call this indeterminate because we can't determine what truly is happening if this is happening. So it's just like 0 over 0. So we have to do a rewrite, and I did a rewrite here. And how I did my rewrite, I dropped a +1, the square of x squared, which I know is absolute of x, and then broke it down as a piecewise as Marie said. So that's perfect. That's exactly what we want to do. Focus on the leading terms. Okay. So we're okay with that?
But,
Yeah. Yeah, go ahead. Go try.
oh, no.
We just ignore like the section in the middle that's like in between.
Right here.
Or like
You-
it kind of like went in the middle, right? When it's like zero at some point.
Oh, you mean the graph?
You can ignore that.
Well, why is that a problem? Just get zero.
You want like the value of the
No, but we're only looking at ends. We're only doing infinity today. Yeah. Okay. So the limit properties still apply. If x is approaching positive or negative infinity, what even these limit properties we had it on the earlier part of the notes when x is approaching a finite value. If x is approaching positive or infinity, you can still use these same limit properties. It doesn't matter. But this is only true when the individual limits, we know what they are. If we know what the individual limits are for these two different functions, f and g, like say one is L, one is M, and if you're doing limit of f plus g, then add those two limits or subtract them if you're subtracting those two functions. Whatever you're doing, just apply that proper principle. And this is all just common sense. So, all right, let's keep on moving. Okay. So sine squared x. Ooh, that's kind of crazy. I want to take a stab how that graph would look. What do you guys think?
The range.
Yes.
Is the range.
From what to what? What
Um,
one is the highest, what's the lowest? Zero, yes. Can never be negative because you're squaring it, right? So the graph will look like this. Obviously, when I plug in zero, I get zero. If I plug in pi over 2, I get 1.
point.
And we get to pi, it's back to 0 again. But then does it go down like this? Because you got to start squaring that, right? Exactly.
Oh,
Yeah, it's like a bunch of hills, rolling hills.
like some
Good question, actually. No, they should be nice. They should be, yeah, because that does come back to something we talk about later about differentiability. Let me think about that one. Pi.
if it's spiky.
No,
It's spiky, that means like you kind of like cut it in half, right?
yeah, it would be actually a corner, right? Because you are flipping it over the x-axis. Yeah, it should be. Well, let me think about that one. That's a good question. Because it happens at pi, right? And 2 pi, and 3 pi, and 4 pi. And there's something that involves a derivative, which I'm trying to do in my head right now. And kind of driving me a little nuts doing that right now. Let's not worry about that for now. Um, but the equation of the horizontal asymptote, well, here's the thing. This is D and E. I don't really know. Sorry, these look like O's. I don't really know what the horizontal asymptote is, right? Because
So
yeah,
none.
yeah, because I just don't know what to say about that, right? Like, I mean, it just goes up, back and forth, right? So I don't really know. Um, as x approaches positive infinity, what's it going to be? Does it ever settle? Does it ever get close to a certain value? No, it does not. It's just oscillating between 0 and 1 over and over again. Yeah, and if I were to go to Desmos, so just to show you guys, yes, that's what happens. Yeah, actually, I think it does smooth out. Yeah, I think it does. Yeah. By the way, what if I do g of x as that?
Oh,
Kind of neat, huh? Kind of like a braid. But what if I do this?
oh, oh, one.
So this is where the limit properties don't apply because the individual limits. F does not exist. G was not exist. But when I added both of them, I did get one because I know this is a trig identity. So in this case, the limit property would not necessarily apply because this actually f of x plus g of x does have a limit. Sine squared x plus cosine squared x is 1. And what's the limit as x approaches infinity of y equals 1? Just 1. So that's just kind of an interesting situation that just kind of good to point to. But for sine squared on its own, it's x. Sorry, it's none. So all right. Now let's keep moving. Let's look at rational functions. So for rational functions, you guys should know this by now. We are going to talk about rational functions in more detail in February or March, I think. But here's what's going to happen. Graphically speaking, actually, we did review rational functions. I take it back. It's a single log and exponentials. We did talk about rational functions. What's happening here was as x gets really large. Yeah, so I think, and there's probably going to be some vertical asymptotes too, I think. I think there's one at 0, or no, it's a whole. I'm not going to, I'm just kind of driving myself nuts to think this through. I don't care what happens in the middle because we're not being asked that question. So let's just do that. Let's just look at the left and right end. Yeah. So it's going to be correct, right? So the limit in each of these cases is 2/3. So y is going to equal 2/3.
What if the degrees
Mhm.
are similar?
We're gonna talk about it in a moment. So in this case, right, the 2x, what doesn't matter, correct? Like, so what you do is you focus on the leading terms. 2x cubed and 3x cubed are your leading terms. So we call this an end behavior model because these are the only things that are going to impact end behavior. And what does that reduce to? 2/3. So that's really what's happening there, is that we're taking a look at only the higher exponents and what's happening. Now, what if I did a slight change here? What if the top was 2x squared? Then what if, say, in each of these cases here? It would be 0.
Mm.
And that'd be 0, right? What if the top were 2x to the 4 power? Yeah, in this case, these are I think positive infinity, and I think it's negative infinity. So there's none. There's no horizontal asymptote. But instead it's a slant, and you have to then go through the motions to solve that, right?
But if it's just asking for a horizontal asymptote, do you just say none and do you
There's no limits. Right, because right. If I ask for it, sure. But there's no yeah, so in this case there's no horizontal asymptote. So let's look at another case here. Now we're going to do this analytically. Because here we just kind of just looked at it from more of a graphical perspective still. Here's how you're going to do this analytically. Um, so I know what's going to happen here is that this is going to be D and E because the numerator is a higher degree than the denominator. How do you do this analytically, though? This part's not terribly obvious, but here's what you're going to do. You're going to rewrite this like this. So what you wind up doing is you wind up multiplying top and bottom by the reciprocal of the leading term of the denominator. Why do you think we're doing that?
Because then you don't have over.
So what we wind up having, what winds up happening is this. And actually, yeah, well, here's what winds up happening. You get 2x cubed minus 7x over 3 plus 5 over x. Okay, if you take the limit as x approaches infinity, okay, if you take those x approaches infinity, what do you wind up getting? Yeah, so the bottom goes away. Why is that equal 0? Because five over a large number. What's 5 over a large number? 0. Yeah, it just goes away. So you wind up getting 2/3 x cubed minus 7x. Now, if you think about that end behavior, right? So we call this our end behavior model.
Why wouldn't it be 7 over 3?
You're right. Sorry, my apologies. So here's the deal. We know the end behavior for these polynomial functions. So I somewhat turned this rational function into a polynomial function. What's the end behavior for this polynomial as x gets large? It's pointing up or down? How about the other one? Correct. So that's going to be the true limits if you want to write that. So are there any asymptotes? No. Horizontal asymptotes, sorry. There are no horizontal asymptotes. But analytically, that's what you would show. You would show that. That's the process. We're going to do that again for example 8, so you guys get the hang of that. I'm looking at time. Okay, we're still looking at time. Let me freeze that for a moment. Let me pull this up in Desmos so you guys see what's happening. So 2x4. So let's see here. Y equals divide 2x4. And what was it? 2x4 minus 7x squared. Down below, we got what? 3x plus 5. Okay, thanks. Okay. Let me clear my screen. Yeah, so you can see here, as you go to the right, it's just going to keep going up forever, right? If I go forever to the left, it goes down forever. So hopefully that makes sense, right? We're cool with that? Yeah.
For these problems here, there's DME 40% possible.
If I do ask for to be more explicit, yeah, I'd want to see that. No, if I ask for if it's positive or negative infinity, then I want you to write that. Yeah. So let's look at the next one here. Now we can do this a little more quickly. What's the highest degree in the bottom? So you're gonna do this 3x cubed plus 8x 5x4 minus x parentheses times 1 over x4 times 1 over x4. The limit as x approaches infinity. And you gotta keep writing that limit notation, very important. Now, that's 3 over x plus 8 over x cubed. What's in the bottom? 1 over x cubed. Okay, each of those fractions become what? 0 plus 0 over, which of course is 0. That's why I get y equals 0.
Do you have to do this process?
Fast for analytically, yes.
Because we know that the rule is that it's.
Correct. But I'm proving to you now why it's true, because now we know about limits and our algebra skills are stronger at this point. So if I do ask for analytical, yes, I do want to see that. So is there horizontal asymptote? Sure, y equals 0. But see, before you guys just memorize, right? You guys, now we see graphically what's happening. We see numerically, we understand numerically. Oh, if I play a large number like 1,000, sure, the bottom gets higher than the top does. But from an analytical perspective, if I do this and use my limit properties and take the limit of each of those individually, 0, 0, 5, 0, I get 0. All right, let's keep moving. So for these here, why don't you guys try these on your own? See how it goes. If you want to use Desmos, go for it. Some of you guys have devices out, or just want to think about it or understand graphically what's happening. So we're gonna do 2. We're gonna do x approaches, and I'll mix like a table. Raise the screen.
Difference if they ask for like numerically find the limit and graph, I mean, and.
Pulling large numbers numerically. Yep. So e to the x, that's exponential. Is that growth or decay? Because e is the number larger than 1, so that's growth. So when x is large, what does y do? Large. So that's going to be infinity here.
So how would you numerically do that? Would you?
I just thought about it. Just pulling a large number. You could show me the number you're plugging in.
R million equals a really big number.
Equals infinity. Yes. Is infinity a really big number? Sure.
Do we have to show?
No, just you can state it. Here's what I did, guys. Well, actually, before we do that, let's just talk it through. If you x approaching negative infinity, is there a horizontal asymptote for this exponential function?
Yeah.
Yeah, all exponential functions do. As you go further to the left, what's y getting closer to? 0. Now, e to negative x, that's reversed, right? Isn't that 1 over e raised to the x power?
Yeah.
Isn't 1 over e less than 1? Hence, that's decay. Since it's a decay function, if x is approaching infinity, that's going towards what? 0. But on the flip side, going towards negative infinity, it's going positive infinity. 1/2 to the x is just like part B, because the base is still between 0 and 1. So part C is the same as part B. Now, for example, 10, what about 5 over x squared? What does that approach as x approaches positive infinity?
0.
How about e to negative x? What does that approach?
0.
So what are you going to be stuck with?
21.
21. Here we go. That's all you have to show. So it's more of a just thinking through. It's a mindset thing. That's all we're trying to do here. Don't overthink it. Like, cool. X is large. What is e to the x doing? Or e to negative x with half x. Oh, x is going towards negative infinity. What are each of those functions doing? And then looking at example 10, looking at those individually, well, a constant's still 7, a 3, that's still 3. But negative 5 over x squared, e to negative x, 0 in each of those cases. Combine it all, you get 21. All right. And I think did I really want to go that far? My gosh. I- that's kind of crazy. Let's get up to let's just finish example 11. That seems to be a little much. I mean, I do want to talk about infinite limits, like as you're approaching the left side and right side, but I don't know. I think that's just a little too much for today. So I'm just trying to see my notes here. I think I want to give you guys like enough time for review for next week. I think that's probably why I designed this way, but it's okay. I think we're okay if we just do one more example and you guys can do the quiz. And then if you guys have individual questions well, actually, we can still talk about homework briefly because we don't get until 11:35. So um, we'll start with this one really fast. So let's rewrite this as a piecewise function. Hope you guys are feeling a little better about that. Okay, we got it teed up here. All right, x plus 5, x plus the negative counterpart of x plus 5. Remember, x plus 5 is an absolute value function. What's the vertex of absolute x plus 5?
-5.
Negative 5 comma 0, okay. So if you think about negative 5 comma 0, the right side of it is positive, the left side it's negative. So when would I use that first expression? What would be true about x if I say x plus the positive counterpart of absolute x plus 5? What would I say? X is what?
Yeah.
Greater than -5, correct. Because if x is greater than -5, you're looking at the right half of it. How about the other one? X is, yeah. And because we're not dividing by 0, we could put inequality next to either one. It doesn't really matter. It's up to you. So I'm going to write it one more time to clean it up. I should get 2x plus 5. And I should get -5. So let's see. That's going to be down here, I think. Gosh, I leave myself no space. And then here, shows the graph. But if they just ask you for this, what am I really evaluating then? The limit as x approaches negative infinity. Which expression am I going to use for negative infinity? I have -5, which course is going to be -5. So that's going to be your analytical work right there. I mean, of course, the piecewise function, we had to rewrite it too. So, yeah, I got to rethink the homework now because I think some of the homework does cover infinite limits as x approaches c. Those are vertical asymptotes, but I could adjust the homework if I need to because, yeah, I'm just trying to think now that for me to do more, I think it's a little too much. I still got 2 more 75-minute classes. So we'll stop the notes for right now. Any questions on the homework that you guys want to ask about? On homework number 6. 5, I think was a little confusing because in order to evaluate it analytically, you had to do the conjugate of the trig functions, and that enabled it to do that using a trig identity. 10, I know we haven't talked much about difference of cubes, but you can use that formula to make sense of that one. And then the rest are all in continuity, I think. No. Any questions on the continuity part of the homework? No? Not at all.
Oh, I have.
Yeah, pretty good. Yeah, good. Mhm. Mhm. Or, sure, sure, sure. Yeah. Yeah, okay, let's talk about that. So removable is when the limit exists, non-removable when it doesn't exist. So in the case of like, say, number 20, right? The quick and easy way is plug in the numbers. So you plug in 2, you get 1 here. Of course, it's 2 here, and it's 1 here. So if you think about the left-hand limit, the left-hand limit is totally going to be 1 as you approach 2 from the left side. The right-hand limit is also going to be 1. But what's f of 2? Something else, right? That's removable. Because graphically speaking, it's going to look something kind of like this. Um, the left and right hand limits exist. That's why it's removable for 20. But in the case of like, say, number 22, that's not. When x does not equal -1, so you have a parabola. Actually, no, never mind, that is. 21 is not, but 22 is. But no, 20, showing it's not. Yeah, so you have a vertical asymptote here. 21, sorry. I already did 20. So 20 is, yes, it's removable. But for 21, you have a graph that looks like this, I think. No, it's the other way around. Yeah, it's like that. And the other side is just going to be a polynomial. If I plug in 1, I should get 4. And it kind of does some weird stuff like that, like that. So in that case, the limit does not exist. The left-hand limit was -infinity. The right-hand limit was 4. Because the left and right-hand limits don't equal each other, that's non-removable. Because you're not removing a point from the graph. 22 would be. 22 would look like this. Vertex. Hold on. Notice that. Yeah, I got it. So 22 is yes, that's removable. Because the limit exists. The left-hand limit equals the right-hand limit. Yeah, that's how I want to think of it. And then if you're looking like graphically speaking for 24, it's removable at 2, but not at 1. That's what's happening for that one.
Jump, it's not removable into this.
Correct. Right. And if 1 through 44 are just like options, right? Correct. Right. Yeah. So anyway, I think that's good enough. Yeah. I'm definitely have to adjust. Well, maybe you guys can still figure out the homework. I don't know. We'll see. Um, well, let me stop the video. I'll have you guys start the quiz. The quiz I did put a 15-minute time limit, but if you need a little more time, that is fine. But still got another 26 minutes of class, but